So you recall we were discussing stacks, and we looked at this example of the use of a stack for the Java JVM, that each time we call a method, a new instance is created, and that frame, together with its program counter, whatever instance variable values are stored, is then put into the stack there. And as those finish execution, those are popped, and control is then returned to whichever method called it, because that will be the next one within our stack. Right. So a very simple way of implementing a stack ADT would be to use an array. We'd store our elements from the left to the right, and we'd keep track of an index that tells us which is the top element. We know that we can add and remove elements from our array on the right very easily in constant time. And by having t there, we know exactly which index to go to do that. Right, and this would be what that implementation would look like. When asked what the size is, would return t plus 1. Since t is the highest index, that would be 1 less than the number of elements that are actually within our array. If we want to add something to our stack, then we would call push e. That would first check if our array is full, because we are using an array which is of fixed size. And there is, if our array is full, we won't be able to push anything extra onto our stack. We'll simply check that and throw an error if that's the case. Otherwise, we increment t, since t is actually pointing to, if t is the last and y is size t plus 1, I just said, t is the last index. The index will be 1 less than how many are in there. Right? Remember, the index tells us the index of any element is how many elements appear before it in our array. So if we have n elements, that nth element will have an index of n minus 1. Simply, you can think of it, we use zero indexing, so the last one will be 1 less than the number of elements there. Right, so if we want to push something onto our stack, because t is actually pointing at the index of the last element within that, we have to first increment t before we use that index. So increment t to t plus 1, then we store e at st. To pop, well, t is already pointing at the correct place, so we'll simply store whatever is at t in e, and then return that. However, if our stack is empty, we won't be able to call pop, so we should first check if it's empty. If it is empty, then we'll throw some error. If not, then we'll simply store whatever is at t within s at e. Then we'll set st to null, and we'll reduce the value of t by 1, since we have 1 less element now, and t minus 1 will now be our new highest index, and then we'll return e, which is the element that was removed from our stack. All right. We could very easily also call peak by simply taking whatever is at st without then removing it. So what's the performance of this if we were to use an array to implement our stack? Well, the space used would be order n, right? Which, while we say order n would be the number of elements, in actuality, because we know when we create an array, memory is allocated for the entire size of the array, and every space within our array is actually first initialized to whatever the default value of that type is. So in actuality, we're using the full size of the array, the full capacity of the array rather, regardless of how many elements are actually in there. Each operation runs in constant time because we're able to add and remove things at the very last index without actually having to change the indices of anything else. So it works quite well. Limitations, well, the fact that we're using a fixed size array means that we have to know how many elements we want to store in our stack, because it cannot be changed once that's been done. And of course, if it then is full and we try to add new things, then we're going to get an error. Another way for us to be able to implement our stack would be using another concrete data type that we looked at before, a single linked list. Right, single linked lists allow us to do arbitrary inserts and removals without having to change any indices or anything like that. So we could actually store or think of the top of our stack as either the front or the back. However, the front or the rear. However, remember that we can do constant time insertions and removals from the front. So we'd store our top item at the front, which means that we'll add and remove things from the front of the single linked list. If we then use our generics framework, we only have to specify what particular type we're going to be storing in this linked list, as we have been doing in our practicals. We'd then have a generic node that we call node stack that represents each node in our linked list. And this would then be like a stack list, a stack implemented using our linked list. There are a couple of applications here. We've already talked about the JVM, the Java Virtual Machine. We're going to look at two different applications that we could use to do this. Actually, the undo won't look at specifically, but for the parenthesis matching, we will look at that. So when you're using an IDE, like Eclipse that we use in class, you'll see that whenever you have non-matching parentheses, because all our data actually goes into, is within particular method blocks, which are within particular classes, we have to have matching braces. If we don't have that, then it'll actually tell you, well, there's a problem with the braces that you have here. You're either missing one or you have an extra one. They simply don't match, or they're out of order. And so how is this done? All right, or have a question, does Java have a built-in stack ADT? Let's see, for the stack, yes, it does. For the queue, no, it doesn't. But yes, it does say we do have a Java stack. All right, so we could have several different types of brackets. This round we call parentheses, our braces, and our square brackets. So if we were to try and match these up, then we could have here different examples. In the first one, note that for each opening bracket or brace, we have a matching close one, and we never have a close before that particular open. So we have then opening round one, closing round one, then two opening round ones, two closing round ones, and then a brace, a bracket, a round bracket, and a square bracket. All these line up. I will never, my innermost one will be matched by my first closing one. I would never end up with like an innermost square bracket and the first closed bracket be a round bracket or brace, then they would not match. So examples, you have the last three ones there. The very first one, I have a closing bracket for an opening bracket. That doesn't match up with anything that shouldn't work. For the next one there, the second correct one, we have an opening brace that never gets the closing brace. And the last one there, simply an opening round bracket without any closing one. So what we'd like is that we would match the first two as correct, and for the others, we should see those as incorrect. And we could actually use a stack to achieve this. All right, so the code will show you here. Okay, you should go through it and convince yourself that it actually works, but rather we discuss what the particular logic of what it does is. And for the most part, what we're doing is that each time that we have an opening bracket, we're going to push that onto our stack. And each time that we have a closing bracket, then we should pop that from our stack. So that means that each time we have an opening one, we push that, we push that, we push that. Then when we get a closing one, we're not going to push that into our stack. Instead, we're going to pop whatever was the most recent thing from our stack and check that it matches that thing, that closing bracket. If they don't match, well, then that means that it's incorrect. All right? And if they do match, then we're happy with that. We continue going to the next one. All right, so before we go through the code line by line, let's see if this would work. So for the top one, I have an opening round bracket. I would push that into the stack. Then we have a closing one. We pop the most recent one, which was that opening one. We check, do they match up? Great, we're happy. Then we move on to the next one. We have an opening one. We push that into the stack. Another opening one, push that into the stack. Then a closing one. So we pop the most recent one, check if those are matching. Great, they are. We now have one round bracket left in the stack. We have another closing one that comes up. So we pop that round one. We check, do they match? They do match. Great. Then we have a series of opening brackets and braces. Each time we push those onto our stack, push. So we push a brace, then a round bracket, then a square bracket, then a round bracket. Then a closing bracket comes about. We pop the most recent one. We check, do they match? They do indeed. So we remove those. Then we have a square bracket. We pop the most recent thing. It does indeed match. The next round one matches the round one. The curly brace matches the curly brace. So those match and we're happy. Then we get to the end of our sequence of parentheses. Are we happy? Not just yet. We need to check. All right, we've gone to the end of the sequence. However, we need to check our stack. If our stack is empty, then we're happy, because that means that all the opening brackets have been matched with closing brackets. If our stack isn't empty, then that means we have an opening bracket that was never matched with a closing bracket. For example, look at the very last one. We push that onto our stack, and then we're at the end of our sequence. However, we never matched that with a closing bracket. Because our stack is not empty, then it's incorrect. All right, so that shouldn't work either. Do we have to pop when we could just peek? Yes, you should pop, because we actually want to remove it and compare. All right, otherwise you're going to peek, compare, then if they're correct, pop it. So you're just going to repeat yourself. There's no reason for that. Please explain using a marker, because I'm lost about the brackets you're talking about. All right, you should understand the difference between a square bracket, round bracket, and a brace, but I will do that. Yes, otherwise you have a square bracket first and a round bracket, and you just peek, the square won't match, yes. All right, if you're simply peeking, not popping, you are going to have to remove them. All right, remember, you can't access anything except what's at the very top. So if you don't take off what the most recent thing that you've matched is, then you're going to end up with things that you can't access below that or beneath that. All right. So for the very first one, let's see why this one's correct. I push this first one there onto my stack. Then when we get to a closing bracket, we don't actually push it onto our stack. Instead, we pop whatever's on top of our stack and we compare the two. If they match, then we're still happy, we continue. We then come to two opening brackets. We push both of those onto our stack. Each time we come to a closing bracket, we pop whatever's at the top of our stack, compare that to the closing bracket. If they match, we're happy. All right. So these two round ones, what's called parentheses, those match with the others, so we're happy. Then here I have four brackets and braces that are all opening ones, so we push those onto our stack. First the curly brace, that's the bottom now, then the round bracket, then the square bracket, then another round bracket. Then I get to my first closing one after that sequence of opening ones. So I'll pop whatever's on the top of the stack. That will be the last thing that was pushed to the stack, right? That is that round one. They match. We continue. We now come to a square bracket. We pop the most recent thing that was on our stack there. It's now a square bracket. We compare the two. They match. We're happy. We continue. We get to a round one. Again, we pop what's on our stack. They match. We're happy. We get to a curly brace. We compare it to what the last remaining thing on our stack actually, but always use the top. We pop that. We compare them. We're happy. We're at the end of our sequence. Is that it? No, we have to check. Is our stack actually empty? If it is, then it's correct. So this first one would be correct. All right. An example where we would end up with an issue is here, the very last one. We push that onto our stack. All right. So we have our stack. We have there this round bracket. We get to the end of our sequence. Okay, great. However, our stack is not empty, so that's not good. All right. Last question. Watch the video again or come to class on time, please. What happens when they match? Do we remove them all? Well, that's what we're doing, right? Remember, pop actually removes it from the stack. So each time I say the word pop, we're removing something from the stack. We don't remove them all. We remove them as they match, right? So as we get to a closing bracket, we pop what's on our stack. That means just the top element is removed from our stack. We compare those two, and if they match, then we continue. We've already done the removal because we popped it. If we get to the end of our sequence of braces and brackets, and we find that the stack is not empty, then we're not happy, because that means we have an opening one that was not matched with a closing one, and that should not be seen as correct. All right? With the second last one, instead there we get to a point where, all right, these three are pushed onto our stack. So first a round, then the curly brace and the square bracket. We get to our first closing one. We compare that to whatever we pop from our stack. That does match, we're happy. However, for the next one, we compare this next closing bracket, this round one, to the top thing on our stack. We pop that, we find that's a curly brace, they don't match. So right there and then we say it's incorrect. And we stop. All right. So if we understand the logic of what we're doing, the code should make proper sense. When all the operations are done, the LIFO principle is still followed, right? Well, it's a stack. It follows last in, first out. We cannot access it in any other way. So regardless of what you're doing on the stack, you cannot access something arbitrarily. You can only ever access whatever was added last. So it's not the operations that we're doing that follow LIFO. The fact that we're using a stack, all of its operations follow that principle, that last in, first out. Right, so this is what we do. We're going from the very first symbol in our sequence here to the last one. That's what the for loop is for. Each time that's an opening one, we'll push onto a stack. Else if it's a closing one, then, okay, we actually should check, can we actually pop? If we're simply to pop, then we'd get an error. We could catch that error and then finish. But it's neater to simply check, is it empty? If it isn't, then we continue. If it is, well, then we have an issue. We have nothing to match. We then pop, check if it's the correct type. If it isn't, then we return false. If it is, we simply continue. Great, now we get to the end of it. If S is empty, then we're happy. That's the only point we return that true, everything matched, it was correct. If it isn't empty, then we still have some opening brackets, but that won't match the closing bracket, then we say it's false and we're not happy with that. If we want to match, if we want to know the number of elements did not match, want the last element that is being popped for comparison affect the number of characters that remain in the stack that did not match. Okay, we have no interest in how many things did not match. All we're doing here is matching parentheses. And if you wanted to know that, you could just say size plus 1. That'd be nice and simple. All right, then what about evaluating an arithmetic expression? We could also use a stack to do this. We have to remember operator precedence, right? We already discussed that when we were talking about Java. We know that multiplication has a higher precedence than addition or subtraction. And we also know that exponents have a higher precedence than that. And of course, brackets have an even higher precedence than that. Associative ones, where it doesn't matter which order we do them in, we're simply going to do from right to left. The idea is this. We're going to push operators and operands, actually, onto a stack, two different stacks. So we'll have a stack that gets values and a stack that gets our operators. You can only push, this is what's going to get the work done, you can only push an operator onto a stack if everything within the stack has a lower precedence than it. If we try, so we peek and we see that the top one has a higher or equal precedence to the operator that we're about to push onto our stack, then we'll first execute that operator on the last two values, get rid of the operator, return the result of that and push that into our value stack, and then continue. Again, compare. Is this one I'm still trying to push onto here of a greater precedence than the one that's on the top? If the one that's on top is of equal or greater precedence, I execute that first. If it isn't, then I can push this onto my stack. All right, again, it's more meaningful for us to look at an example before we look at the code. All right, so just note that we're going to have two stacks, op stack, which holds the operators, value stack, which holds the values. The special end of line input character, we're going to say has the lowest precedence. So that means that actually, when we get to that one, we have to do everything that's within our operator stack because there's nothing of a lower precedence than that one. All right, input should be this expression. Output should, of course, be the result or the value of that expression. So here, let's take a look. We have several different operators. Let's recall that logical ones, like the one that we have here, less than or equal to, has a lower precedence than all the others, really, besides the special character that we defined. So lower than addition and subtraction, which is in itself lower than multiplication, which is lower than exponential notation, which is lower than brackets. All right, so we're happy with all that. We can now go ahead because we know the operator precedence. So we begin. First thing that we come across is 14. We push that onto our value stack. Then we come across this comparison this logical operator less than or equal to. There's nothing within the stack, so we're happy. We can just push it into the stack. Then we come across 4, we push that into our value stack. We come across subtraction, we compare. Is everything, or is the top thing within this stack of a lower precedence than subtraction? Yes, it is. So we can push subtraction onto there. Then we come across 3, we push that into the value stack. We come across this multiplication operator. We check, well, is what's in the stack less than, have a lower precedence than it? We compare with the top one, we see subtraction is of a lower precedence than multiplication, so we can push multiplication onto the stack. Then we get a 2, we push that into our value stack. We get addition. This is the first instance where we actually see that the operator that we're currently trying to push onto our stack, right, that addition operator, has a lower precedence than multiplication. So we can't push that addition one onto our stack. We first have to pop that multiplication and apply it to the last 2 values in order. So what we want to do is pop that 2, put that at the right of our expression, then put our operator there, then pop the 3, and this is what we're going to evaluate. 3 multiplied by 2. That's equal to 6. So then we replace those 2 values that we popped off, or rather we push this result onto our value stack, the 6. The multiplication we don't put back in there. All right. Question, how do you know which operator has a lower or higher precedence than the other? You must certainly have learned this in high school, or in fact primary school perhaps. I don't know if you still call it BODMAS, but that's what we called it, brackets of multiplication, addition, multiplication, division, addition, and subtraction. That brackets or parentheses have the highest precedence, then of which represents exponential notation, then multiplication, division, addition, and subtraction. All right. And we've said logical ones have a lesser precedence than addition and subtraction, and the special character at the end of our sequence has the lowest one. All right, so now we've just replaced, so we're now busy here. We've just replaced our 3 multiplied by 2 with a 6. All right, so the result is pushed onto the value stack. The operator is not put back into the stack. We still want to push that addition into the stack. However, addition and subtraction have the same precedence. And we said we can only push it when the things in the stack have a lower precedence than it. So we still can't push addition into the stack. So again, we pop the 4, pop that operator, subtraction. Oh, I did it the wrong way around. The top thing was 6, not 4. So first we pop 6, then the operator, then the 4. All right, and we do it in order. So it's 4 minus 6. That gives us -2. We then push that result onto our value stack. Then we check. Again, we're still trying to push addition onto the stack. Is what's in the operator stack of a lower precedence than addition? Finally, it is. So we can push addition onto the stack. Then we get to 7. We push that into our value stack. Then we get to the end of our expression. That has that special character, this dollar here. And so now, can we push dollar into the stack? No, because it has the lowest precedence. We actually have to do everything that's left. So we do it in order. We pop -2, that goes on this side. We then do our addition and 7 there. What is the special character? It's a little dollar here. Okay, if I go back 2 slides, but I don't want to get rid of the annotations yet, then we agreed that the end of line character will have the lowest precedence. All right, that's where that dollar came from, or that dollar symbol. So we actually pop 7, -2, apply addition to those. We end up with 5. We push the result onto our value stack. Then we have that logical operator. That, of course, has a higher precedence than this end of line character, which has the lowest precedence. So we have to apply it. 14, is that less than or equal to 5? The answer is no, that's false. And so we replace, or rather we take that result of false and push that into our value stack. Now we're at the end of our sequence, and we've actually executed all of those operators because there's nothing on our operator stack. So what remains in our value stack should be the answer, right? As in should be the value of that expression. And that is what we'd get. If we simply look at that expression, we know multiplication has the highest precedence. Straight away, we can replace those two with 6. 4 minus 6 plus 7 is 5. Is 14 less than or equal to 5? No, it isn't. So false is the correct answer. All right, so just to satisfy that question, we're using dollar to represent that special end of input token, which has the lowest precedence. All right. Is there a Java method which identifies which operator has lower or higher precedence, or we have to know and hard code it? You could easily set up your own comparator to compare two different operators, right? Whether Java has a built-in one, I don't think so. Is there a library that can do that for you? I'm sure there is. Right? However, you could very easily set up your own one. You're going to have to then accept strings, check if there actually are operators, then say which is greater than the other. Then you can simply call that comparator whenever you want to compare two operators, and it will give you the notation of a comparator. So it'll give you 1 if the one is greater than the other, -1 if it isn't, and 0 if they're equal. All right, so let's actually look at the algorithm. We have here a method doOp, which pops a value from our value stack, then pops another value from our value stack, pops an operator from our operator stack, and then does in order the second one that was popped, operator, and the first one that was popped. All right, which is the order that we were taking when we were doing the example. Then another method, repeat operators or repeat operations. And this is past a reference operator. Now, what we're doing each time is we're looking at what's at the top of our stack. So just look at here. What's at the top of our stack? Is that thing, does that have a lower precedence than the reference operator or we're trying to push onto our stack? And we will do this for as long as that is true. As long as the precedence of what's in our stack is greater than or equal to the reference one, then we'll continue to do that. All right. This is all right. So there are two conditions: is there something on our stack? So the size is greater than 1, and do we have this particular issue, or do we have this condition where the precedence of what's at the top of our stack is greater than or equal to what's less than what we're actually trying to push onto that stack? If this condition was never true, then operators won't be done. You saw that each time that we had something of a higher precedence that we're trying to push onto our stack, you can simply go ahead and do that. If that isn't the case, then we have to actually do the operation. So execute with the last operator on our op stack with the two top values on our value stack. And then to evaluate the expression, as long as there's another token, so as long as we're not at the end of that line, we check, is that token a number? If it is, then we push that into our value stack. That makes sense. If it isn't, then we try to push it onto our value stack. Or rather, before we try to push onto our operator stack, we have to compare. So we call that repeat ops. That repeat ops asks us, is there something within our stack, and is the precedence of the one that we're trying to push onto there greater, or rather, is it less than or equal to the one that's at the top of my stack? If it's the one on my stack is greater than or equal to its precedence, greater than or equal to the one I'm trying to push, I have to actually do operations. If not, I can just push that onto my stack. All right. Then we'll repeat ops and pass that the end of line character, which will simply do the operations over and over until there's only one thing remaining in our value stack, and that will be the answer. And that's how we'll then repeat the top of, or rather we'll return the top of our value stack. All right, note that at 19, that will actually do the operations regardless, because that has the lowest precedence. Okay, that special character we've agreed, which represents the end of the line, will have the lowest precedence. All right, so we're convinced that that works. So we're going to move on to another ADT. You have dealt with a concrete implementation of this before, but now we're talking about in the abstract sense, what is its behavior? And again, we'll see that we can use several different implementations to achieve this. All right, you may have noticed that of the last few ADTs that we discussed, All right, I believe we've discussed three thus far. We talked about a list, then a stack, and now a queue. These are all ADTs that store a collection of elements and have some concept of order. All right, in fact, they all have a linear order. And our list was the most general of the three. Our list allowed us to do arbitrary inserts and removals. However, the stack only allowed us to remove and insert at the top of our stack. So it was more restrictive than our list. And we'll see that the queue is quite similar. It also only allows us to add in at one point and remove at the other point. And so, again, it's a collection of elements that has this linear order, but it isn't as general as our list. So why do we have it? Well, it models a real life queue. All right, it's something that actually comes up a lot, whether we're talking about in physical life when you're queuing for service at a grocery store, at home affairs, or if we're dealing within a machine and we have some sequence of requests coming in and we have to service those requests. Again, we would like to do those in order. So if the one that got there first should be serviced first. All right. Or waiting list for applications for applicants. Yes, I mean that could be at a bank, anywhere would want to follow FIFO, that whichever arrived first should be serviced first. Right, so again, it stores this collection of arbitrary objects. All right. However, insertions and deletions have to now follow FIFO. They can't be arbitrary. Whatever got there first has to leave first. So what we'll do is that we will insert at the rear of our queue, and removals will be done at the front of our queue. All right, and that makes sense because the one that was inserted first at the rear will actually be at the front. The next one will be at the rear. The next one, the new rear, and so on and so forth. And the removals will start at the front. That'll be the one that arrived there first. Then the next removal will get the one that arrived second, and so on. All right, so the main operations of our queue will then be enqueue, which is to add something to our queue. It inserts an element at the rear or the end of our queue. Dequeue, so to remove something from our queue, will return and remove the element stored at the front of our queue. All right, there's some others which we have equivalents in our other ADTs. Size and is empty, and front will return the element at the front without removing it. All right, so similar to our top or peak that we have for our stack. We can have exception if we're trying to dequeue or remove or return the element stored at the front. So our front on a queue that is empty, then we should throw some exception because we can't return something from an empty queue. All right, so an example of how it should behave. If we're in queuing 5, that's added to the rear of our queue. Note, because we only have a single element there, it's also the front of our queue. And Q3, it's added to the rear. DQ should return what's at the front of our queue, and that was 5. So that works. And Q7, that adds 7 to the back of our list, the end of it. DQ should then return what's at the front, which is 3. So we're happy with that. If we simply call front, so at line 6 there, this will return but not remove what's at the front of our queue. So it returns 7, but 7 is still within our queue. We're happy with that. DQ then returns 7. If we try to call DQ again on a list that's now, or rather on a queue that's now empty, so this queue is empty, we try to call DQ in the next line, we should get an error because it's actually empty, we can't do that. The same thing would happen if we were trying to call front on that empty queue. Is empty should return true at that time because our queue is indeed empty. Then in Q9, it goes to the back of our queue, which is also the front, and Q7 adds 7 to the end of our queue. Size at that moment will then be 2 because we have 2 elements stored within our queue. Then we NQ3, 3 is added to the back of our queue, we NQ5, 5 is added to the back of our queue. Then if we call DQ, the front element, which is 9, is removed and returned to us. Right, so that is the behavior that we expect. How can we then achieve this? All right, first things first, if we use an interface to express the behavior of this queue, we would have the methods that we discussed. Size, which returns an integer that represents the size of our queue. Is empty, which returns a Boolean, whether or not our queue is empty. Front, which can throw an exception because if that's called an empty queue, that can't return anything to us. it should then return something of type E, so an element that's stored within our queue. NQ, we have to pass that something of type E, but it doesn't return anything, simply returns a void. And then DQ, which again can throw an exception, and it should return to us something of type E. All right. So we do then have to define what this exception does, what information it returns to us. And for this, there isn't a corresponding built-in Java class, but we can certainly implement it ourselves easily. Why do we return the removed or inserted element? Why do we return the removed or inserted element? All right, the inserted one we won't actually return. Note that for NQ, the type is void. For the removed one, we may want to do something with it, right? Ideally, we're supposed to be servicing that request, so we shouldn't just throw it away. We want to return it so you can actually do whatever it is that's equivalent to servicing this request. Whether that's displaying that number on a monitor that tells the next client to come to whatever service desk, or whether that means you are taking that frame and actually allowing it to have access to resources and run for some period of time. Whatever it is that is equivalent to servicing those requests has to be done on that element that's returned. How do we define this exception? Well, if you're lazy, you'll simply have all the constructors of your exception just call whatever superclass it extends. If you want to do more, then you can actually have a meaningful message passed within that to say, well, okay, it's empty. And then, of course, in your catch block, when you catch that type of queue, because it is a specific type of queue for the data type that we're working with, you can decide on what you want to do for that. So within your program, perhaps if it's empty, you simply want to say, okay, it's empty, we end execution there. Or more likely, if that type of error is caught, you want to say, well, our queue is actually empty. What would you like to add to our queue? So remember that we said that our programs should be robust, they should fail gracefully, and that means that if you have that type of error, you should actually deal with it in such a way that we can continue execution. All right. So direct applications, waiting lists. Certainly, if you've ever been to Home Affairs or a bank or anything like that, you'll note that nowadays, even pharmacies, you take a number, a slip of paper that represents the number that you are in a queue. When you're not at the front of that queue, then your number will be called. All right. Oftentimes at a bank and other places, they'll give you an estimate of the time that it'll take for you to be served. This simply looks at how many people are within that queue and the average service time. So you can do some very interesting things with that. Then access to shared resources, another example. So like your printer spooler, as different machines within a network request documents to be printed at a single printer, because printing is a lot slower than requesting a print job, those jobs should be put within a queue that services them in FIFO fashion. And that's our printer spooler. All right, oftentimes you'll be able to just double click on that little icon on your desktop and it'll show you how many jobs are actually in front of yours, and that gives you an indication of how long it'll take for yours to be serviced. Then multi-programming. Remember we talked about this example that even before we had multiple core machines, we could still run more than a single program on a machine, and that was achieved through multi-programming by storing the state of different applications and giving them access in that round-robin fashion to resources for a limited period of time. And of course, we could use this auxiliary data structure for other applications. So our first implementation of a queue, again, we start with our simplest type of data structure that is built into most languages, and that's an array. So we could use an array of size n. Because now we aren't adding and removing from the same side, it won't be sufficient to simply store things left to right and add and remove from the right. Now we want to be able to add from one end and remove from the other. So the simplest way is for us to use this array in circular fashion. Now we'll have to keep track of two variables, a front and a rear of our Q that is stored in this array. We remove things from the front, which means we access that index front, return whatever was stored there. If we want, we'll set that to null. Then we increment our front, so that now points to the new front of our queue. If front and rear happen to be equal, then we know that it's empty. If it isn't, then rear will still point at something else. We can then, well, we have two options. We can either have rear pointing to the very last element within that array, in which case we'll have to increment it before we store something there. But what we'll do is we'll actually have R pointing to the next open slot, because then we can always compare and see, well, if R ever gets to F, we're going to have an issue, right? If R gets in circular fashion and comes back to where F is, then we can have a full queue because we're using a fixed size data structure like an array. Right, so the array location R will be kept empty. And of course, if it isn't empty, then we have an issue because we realize we've actually wrapped around. So this is what we expect to have. The normal configuration is when we're simply using the array in order there. So we have some front F. So it seems we removed already 4 things from our particular queue. We have R there, which is kept empty, which is 1 plus the highest index. When we get to the end of our array, we'll then wrap around. So we'll be using modular arithmetic on the size of our array to make sure that when we get to the end of it, R simply then goes to the next, which would be the 0th spot within our array. And that works as long as our array isn't full. All right, so again, we'd have to know how many elements we want to store in this queue beforehand, which isn't always possible, but if we know the type of situation we're dealing with, then we could do that. Okay, certainly looking at past behavior, we could tell, for example, what is the longest waiting, what's the longest queue that we end up with at our particular, whether it's a pharmacy or a bank or whatever else. By looking at the rate of requests coming in, the rate of service, we could tell what the maximum length of our queue would be. All right, there's a whole science associated with that in theory, which looks at those types of issues. Okay, I was getting a little feedback there. Please make sure that your mics are muted. All right. So our queue operations, these have to be done if we're using an array using modular arithmetic to make sure that when we get to the end of our array, we actually wrap around and go back to the beginning of it. Our operation enqueue can throw an exception if our array is full, and that exception will be implementation dependent. The operation dequeue can throw an exception if our queue is empty, and this exception is specified by the QADT, because that can happen regardless of implementation. All right, so what would these look like? Our algorithm for size, because we're using this modular arithmetic, we can't just, or rather because we're using 2 indices, front and rear, we can't just look at one of them to determine what the size is. What we're going to look at is n, which is the size of our array, and then we simply subtract from that where our front is and add to that where our rear is, and that tells us what size we actually, or rather how many elements we actually have within our array. All right, so what we're subtracting is the open spaces between our front and our rear. Then this should be done mod n, because if they're wrapped around, then we're going to get that our rear will actually be behind or smaller than our front. And so we end up with a larger negative value there. And so we'll take mod n to give us that. All right, well, we'll end up with 2 negatives, and that makes it larger than n, so we do mod n to get that size. Then is empty, well, if f is equal to r, then it's empty. All right, nothing's actually stored within that. NQ should first check, well, do we actually have enough space to do this? So if it's full, if n minus 1 is equal to our size, then we actually don't have space to store things, because remember, we always want to keep R empty. So then we would throw an exception that says that our queue is full. If that isn't the case, then we'll simply store our element at R, and then we increment R mod n to make sure that it wraps around. So if R was already in, R plus 1 mod n will just give us our 1 again. All right. DQ, again, if we have nothing in there, we should first check, is it empty? If it is, then we throw an exception because we can't DQ something from an empty queue. If that isn't the case, then because, remember, we DQ from our front, we take whatever's at the index F within our queue, we store that in a temporary variable, we set that index or the space of that index now to null, we calculate our new F, again, mod n, and we return that value using our temporary variable. Right, so we have one more ADT that we want to look at, which is a double-ended queue. This allows us to be able to add and remove elements from both the front and the back of our queue. All right, so we have add first and add last, not just our add last. And we have remove first and remove last, not just the remove first that we had in our single-ended queue. All right, this is called a deck. What does big N represent? The capacity of our array. So how many elements could actually be stored within that array? Again, we have sizing as empty, but now instead of just having get first, which returns without removing the value stored at the front of our queue, we now have get first and get last. So we can access both the front and the back of that queue. The runtime of our operations, well, size will be constant time, simply returns to us how many elements are within that queue. Is empty as well, should be constant time. Get first and get last, even if we're using array, would still be constant time. Add first and add last will be constant time as well. And remove first, remove last will be constant time as well. All right, so we'll be happy with this because none of our operations actually depend on the number of elements stored within that queue. They can be done in constant time. What would the behavior of our double-ended queue look like? Add first would add something to the front of our queue. Granted, if it was empty there, 3 would be at the front and the back of our queue. Add first 5 now does something different to what our single-ended queue would do. For our deck or double-ended queue, it would add something to the front there. Remove first removes from the front and returns that value. Add last now adds to the end of our queue. Remove first removes that 3 from the front of our queue. Remove last, well, there was only a single thing in there, but it removes what was the last element stored in our queue. If we call anything like remove last, or sorry, like remove first, or even get first from an empty queue, we should get an error there that it's empty. Is empty would then return to us true because our deck is indeed empty. All right, and we can implement our round-robin scheduler using a queue by repeatedly performing the following steps. E would simply dequeue whatever is the frontmost service, the one that arrived first from our queue, service that element, so allow it to have access to resources, then enqueue it, which adds it to the end of our queue. All right, we actually already looked at that. We understand that now we have our QADT. By simply calling these two methods and between them actually servicing that request, we can achieve that round-robin scheduler that we discussed before. What would that look like? So simply we dequeue from the front, give it access to whatever resources actually service this query or this request, this application, and then add it to the back of our queue. And this will achieve what we want. All right, again, we have some exercises for you to do. Just note that although this is the 4th lecture, the chapter that it corresponds to in the new text is the 6th chapter, and that's why we have these examples that are numbered 6. Okay, are there any questions of the two ADTs we discussed thus far? That's the queue and the stack. Okay, which is the next ADT we're learning? Well, you're about to see that just now. What we're going to look at is actually the list ADT that we discussed before. We're going to look at two ADTs that are kind of extensions of that one. So we're going to introduce the concept of an index into a list, and we'll see we end up with what we call an array list or an index list. Note that's not the same as the array list that we use in Java. Unsure why we're using mod. Okay, we'll look at an example then. When can we expect to receive feedback on our proposals? Well, ideally by the end of the week, but I'll have to consult Prof. Van der Haar and we'll split that work. But in the next few days, you'll get feedback on that. All right, so someone asked why mod. Let's take a look. If we have, okay, let's go back perhaps to, no, all right, we'll just do that here. Let's see, if we have an array, all right. Okay, so the indices should be 0, 1, 2, 3, 4, 5. All right, so we have this array that has a size of, well, capacity of 6. The highest index that we expect to end up with here is 5. If ever we end up with an index greater than that, well then, if we weren't using this in circular fashion, we'd end up with an array index out of bounds error, right? We wouldn't be able to do that. So if we set n to represent capacity minus 1, so the highest index that we could get, then n would be equal to what? Our length, which is 6, minus 1, which is equal to 5. So any operation we want to do that has to do with indices, especially incrementing indices, would want to take modulo 5. So if we want to take, oh no, that's incorrect. N, I already said, was supposed to be set to the size of our array, not to the capacity, not the size. All right, so it's just there 6, apologies. All right, so if we want to have, let's say we are adding things to our queue. So we added something here, all right, so our front is now 0, our rear, which is kept empty, is 1. We add something else, we add something else, we add something else, we add something else, we add something else. When we get here and we want to get our R to point to the correct place, then R, which was previously 5 here, we want to now become 0. What do we do? If we take R plus 1, that would end up with 6, which is not actually allowed as an index, which is not an index that will be allowed without getting an error here. If we instead take that mod n, so mod 6, 6 mod 6 is equal to 0. R is now the correct value. All right. Then can you please post end of chapter questions on like did lecture 1? Some don't have international version. All right. Note though that the questions are very similar. There are only a few different ones, and the project ones are different. So you can use the old one. You can simply go through those exercises. All right, but I will post the ones for this lecture. All right, so doing modular arithmetic simply ensures that we don't end up with invalid indices. All right, I trust that answers that question. And while you type in any other questions you may have, we're going to begin on the next lecture. All right, I don't see any questions at the moment, but as always, if you have any questions, just type them in there. We'll address them as they come up. All right, as for the proposal, what will happen to students who haven't registered? Well, if you have submitted your proposal, you've seen you don't actually need access to do that, then we'll find some way to give you feedback. We can either email it back to your student email address, or more likely we'll simply post that somewhere on Eve because everybody has access to that. But I would expect in the coming days, everybody should be registered. All right, as far as I know, Friday is the last day for registration. Um, and in fact, for senior students, you should already be registered at this stage, though it was extended for first years. Um, I would expect that everybody within here, including the person who asked the question, I know for a fact, are registered for the module. All right, so we are going to be looking at the next ADT, which is we're looking at two different ADTs that are kind of derivatives of our list ADT. The first is an array list. Please note this is not the same array list, which simply represents a growable array in Java. This is what's also known as an array-based list or an indexed list. It adds the idea of an index to the concept of a list. Then we'll look at a positional ADT, a positional list ADT, and iterators. All right, then we'll look at our sequence ADT, which is closer to what is termed an array list in Java. So please, from now on, when we talk about array lists, we're talking about the type of array list that we're discussing here, not what you expect to find in Java. All right, so you remember our list ADT, which was what? A collection of objects that have some ordering, all right? A linear ordering that allows us to be able to do arbitrary inserts and removals. So our array list ADT is simply going to add the concept of an index to that idea of a list. So we still have this collection of elements with a certain linear order. This can also be called a list or a sequence. We won't use the term sequence because there's a separate ADT that we call a sequence. And if we add the idea of an index, right, that we're able to refer to an element within that list by using the index, which is simply the number of elements that occur before it, then that makes it this array list of ours. All right. Note that this type of sequence is also known as an array list or vector, which is an older term, but it's not equivalent to the array list that we have in Java. Some texts will use the term rank. However, we don't use that because that is actually ambiguous. Rank can refer to the rank of an element, which is usually what would the index of the element be if we had a sorted list. But even how that rank is derived for repetitions is different depending on different texts, and it can also be used to refer to simply the dimensions of an array. So a single dimensional array would have rank 1, a 2D array, so an array of arrays would have rank 2. So we don't use the term rank, instead we use index, which is well understood regardless of context, that the index of an element E is the number of elements that occur before that element E. So our first one will have rank 0, also will have index 0, because there are no elements that occur before that. And if we have n elements altogether in our list, the last one will have index n-1 because there are n-1 elements that occur before it. All right, so that's well understood, and that's what we use. So the main methods are array list. You see now that we use an index to access elements within our list, and also do operations like adding and removing from our list. So get I should return the element stored at index I without removing it. Set I will either, if there isn't anything stored at I, and only under a certain condition, when I is actually 1 plus the highest index, will then store E at that new index, or if there's already something at that index I, will then replace the value that's stored or the element that's stored at that index I. Add IE will then add E at index I. Remove I will then remove the value or the element stored at index I. We have some supporting methods, size, which returns the number of elements stored within that, and is empty, which should return whether or not our list is empty. All right, there was a question. What if index I is out of bound? Then we should return an error. All right. So there's no restriction on using an array to implement an array list. What is important is the index definition. All right, so understand that we are although we're using this concept of an index, which comes from arrays, an array list is simply a list as we understood it before, with the concept of an index added to that. So we can now access and modify elements within our list using an index. However, it doesn't mean we have to implement it using an array. We can implement it using a variety of concrete data structures as long as we're able to implement all these methods that we are discussing. All right, I see a couple of questions asking for a little more information on set and add. That's what we'll look at in the next couple of slides. Okay, that's exactly what we want to investigate. Okay, before that, we will be using a particular design pattern that you're already familiar with, but just because we don't expect that you remember all that, we want to reiterate. You'll recall the adapter pattern. In a different contexts is also sometimes called the wrapper pattern, which is when we create a new class by using an existing class to provide that new functionality. So an example is using a linked list to provide the stack functionality, right? Or using an array list to accomplish a deck. So if you had already implemented one of these ADTs that we discussed, so let's say you implemented the most general one, a list, we could use that list to provide the functionality of a queue, a stack, or a deck. What we'd do is we'd create a private instance of that list and only allow the behavior of the new ADT that we're trying to implement. So if you were to, for example, let's say we're trying to create our stack, that's a simple one. We want to be able to add and remove from one side, and we'd already implemented our list. We would simply allow the behavior of adding to the front and removing from the front to be exposed. The rest of the behavior of a list, which are arbitrary inserts and deletions anywhere on our list, would not allow. So we would create a private instance of a list, and then we would implement, I said in inverted commas, that push and that pop of our stack by simply calling for push, add or insert at front, and for our pop, remove front. All right, so we wouldn't have to now create from scratch a new implementation. If we already have one that's implemented, we can use that to now create the behavior of a new ADT. You should have used the data pattern before, but as we go through, we'll look at examples of that. Right, so one way of implementing an array list or array-based ADT, array-based list ADT would be expectedly the simplest way to use an array to store these values. Okay, if we use an array, then AI would store a reference element with index I. Someone asked, what is a deck? Well, we just discussed a double-ended queue, that's a deck. So AI now stores a reference to an element of index I. So our algorithms for add I, E, and remove I will be straightforward. We'll look at the code fragments for that. The performance for everything is constant time, except for add and remove. Why? Because when we add and remove things from our array list, everything that occurs after the new element that was added or removed has to now either have, if we're removing, its index decremented, or if we are adding, have its index incremented, because there are now either fewer or more elements that occur before it, right? So if we had an element with index 5, so that tells us there are 5 elements that occur before it. If we were to remove one of the elements, this element that had index 5 should now have index, so that now have index 1 less, should have index 4. If something was added before it, its index should now increase. Otherwise, we're not able to call that or to have access to that element by simply indexing into our array at that particular index. We have to make sure that we keep track of those indices because they change as things are added or removed before those elements. Right. So our add and remove will be order n, although it's not actually order n because we're not going to be moving everything, simply the things that occur after that ith index, because they are now changed. So it'll be order n minus I plus 1, but that is equivalent to a linear time algorithm. So adding and removing will run in constant time, or the adding and removing at the end runs in constant time because it doesn't change any of the things that occurred before it, and there's nothing that occurs after it. Whereas adding and removing from our front will now take order n time because that means everything within our array list will have to have its index changed. Right, and the consequence of using our array list with arrays for a deck, so that wants us to add and remove from both the front and the back. Well, from the back, that's very simple, there'll be constant time, but all our operations that want us to add at the front and remove at the front, those will then be order n time, which isn't great. All right, can we then do this in constant time? Can we do it in order 1 time? Well, if we use this array list, so again, we have to have fixed capacity because we're using a fixed capacity data structure. So we have to know what's the greatest size that we're likely to work with. That would be n. All right, there's a question, I assume. Someone has raised their hand. You can go ahead, lower your hand and ask your question. Either put on your mic and ask it verbally, or you can type into the chat. Okay, I assume you're typing in, so I'll continue until we. Oh, okay, that's fine. That was an error. That's fine. Right. So variable n will keep track of the size of our array list, so simply the number of elements stored within that. Operation get I, because we're simply returning without removing something from our array, will be constant time. We simply index into our array at I and return that particular value. Set I, which we said, will simply replace what is stored at I. That'll be constant time because your index into that, perhaps store that into a temporary variable that you want to return. Then that new value O is stored at that index AI and returns it. All right. All right, we haven't quite gotten to the point where we discussed the subtle differences between set I and add I. So let me just discuss that since it may be keeping you from fully understanding it. So set I should replace whatever is stored at index I. All right, that'll be constant time. It simply replaces what was put there. Whereas add I should actually insert at that position I, and everything that comes after it, in fact, including what was there before, will be shifted to the right by 1. So adding won't take constant time because you have to change the indices of everything by actually moving them up in our array, whereas by setting, we're simply replacing what was there. Right. However, if we're adding at I the end of our list, then it will be constant time. Similarly, for our remove operation, if we're removing from an index, everything that comes after it should be decremented by 1, its index. So we'll move that left in our array to fill up that spot. But if we're moving from the end of our array list, then it'll be constant time with an array implementation. All right, hope that clears it up. And we're seeing that now. That for our set 1, because we're simply replacing what's there, that'll be constant time. For our get, we're not actually removing anything from our array, we're simply returning what's there from our array list, then that'll be constant time as well. However, now for things where we want to add remove. All right, so we have a question. What happens if we remove or add, but don't increment or decrement? Well, then the indices are now incorrect. All right, if you simply have, let's say, 5 things within our array list, so 5 elements, indices 0 to 4, and you remove what was at index 2. The 2 other ones at index 3 and 4 now no longer have index 3 and 4 because there aren't 3 elements before the one that had index 3, and there are now not 4 elements before the one that occurred at index 4. They have to be changed. What had index 3 will now have index 2, because one of the things before it was removed, and what had index 4 will now have index 3. So we can either store another value with each of our elements and increment or decrement that, but it's easier for us to simply move them in our array because that keeps our constant time accessing of elements. Where we simply have that when you want the element at index I, you will index into your underlying array at index I. So if we don't keep those consistent, we can't simply index into our array to get the value that within our array list has index I. Right. Then if we add there is something at I, do we shift it? Well, if there was nothing at I, then as in if it was at the end of our array list, then no, nothing needs to be shifted. If it was within the elements of our array list, somewhere in between the beginning and end, then yes, everything has to be shifted to the right. If we're instead setting what's at I, then no, we'll simply replace what's at I. Or since there's something equal to set, no, the setting would actually replace, it wouldn't move the others, but for adding, we'd have to move the others. What happens if no space to shift? Well, then it's constant time. All right, we're at the end of our array list, then we simply add at the end of our array list, nothing needs to be shifted. Would increase number of elements to make more space? I don't know about making more space, right? If we're using an underlying array, then that has a fixed capacity. We can't make more space. Right. The number of elements that we can have in our array list is now limited to the capacity of our array. Let's just note that. All right, so let's actually look at an example of adding at I. So the operation add IO, so we want to take this new element O and add it at index I. We need to make room for that by shifting all the elements forward by 1, and only the ones that actually occur after I. All right, so that will be the n minus I elements that occur after I, from I to the end of our array list, which should be at I n minus 1. All right, that effectively changes their index, which is correct, because they now have one more element before them. In worst case, if we're actually trying to insert at the beginning of our array list, then this could take order n time. Why? We actually have to shift everything that was in there 1 to the right. All right, so this is a diagram of what that would look like. We have our array list. Note the elements from I up to n minus 1 are colored in blue there. Those will all have to be shifted to the right before we actually insert O at index I. And now all their indices have been changed by 1. And if we now index into I plus 1, we'll find what was previously at I, which is correct because its index has been incremented by 1. There is one more element that occurs before it in our array list. All right, so we note when we are either inserting, so adding or removing elements somewhere within our array list, then we'll have to shift all the elements that occur after it, either 1 to the right if we're adding, or 1 to the left if we are removing. Worst case, we're adding or removing from the beginning of our array list, in which case we have to shift all n elements either to the right if we're inserting, or to the left if we're removing. So for our remove one, if we're removing at I, everything that came after I now has an index 1 less. It'll be moved to the left. Note that here we don't actually have to, we would store our O because we're removing that, so whatever was at index I into a temporary variable, and then simply shift everything 1 to the left. All right, there's a question. Since an array doesn't resize, if we adding an element, do we then make a new copy of the array? All right, if you wanted to make your array growable, then you would have to do that. At our current understanding, our array has a fixed size. So if we're implementing our array list using an array, then when it's full, it's full. We'll throw an error. We wouldn't currently do anything. We will get to how we resize an array, but at the present moment, we are limited by the capacity of our array. The array list itself doesn't have the concept of a limited capacity, but if we're using an underlying array, then when it's full, we'd have to throw an error. Okay, we will look at what if we wanted to make it a growable array. All right, so for this array-based implementation, the space used by the data structure is order small n. We know in actuality it's order big N. It's actually the capacity of the array because everything is actually allocated and first sets the default value. That's fine. Size is empty, get and set run in constant time because get simply returns without removing, set simply replaces, so we're fine. The add and removes, however, can run at worst in order n time because we may have to move everything within our array to make space for the new element we're adding at 0, or if we're moving from 0, everything has to move one to the left. So n-1 things will be moved one to the left. All right. If we use our array in circular fashion, then we can actually get adding and removing at 0 to run in constant time. However, everything in between will still take some number of shifts. So we can get add 0x and remove 0x to run in constant time. And in our add operation, the array is full, we can throw an exception, but if rather than doing that, we want to grow our array, then note, an array can't actually be changed. The size or the capacity of our array can't actually be changed. So what we'd have to do is we'd have to create a new array, copy everything from our old array into that new array, and then throw away that old one. All right? So there is no way to take something of fixed capacity and actually grow it. Instead, we'll have to create a new larger array and copy everything over into that. All right, so now that we want to deal with this concept of this growable array, we understand that in actuality, you can't grow it. You'll have to create a new array and copy everything over into that new array. How long will our add operation now take? So when our add operation is simply adding to the end of our array, and in fact, add O that does not have an index, that method will simply add to the end of our array list, which if we're using an array, simply adds to the end of our array. Then if our array still has space, that'll be constant time. However, when our array is full, we'll replace our array by a larger one. How large should this be? We have two options for this. We can either incrementally add a constant number of additional spaces, or we can double the size of our array. Which do we think is better? Which will have a better performance? Doubling the array each time, or incrementally adding a fixed amount of new spaces each time? Intuitively, what do we expect? One says doubling, doubling, doubling. Okay, doubling. Someone says incrementing. All right, adding a fixed amount and doubling. Great, so we have people who think that the incremental strategy will be better and those who think that doubling strategy will be better, which is good. We'll take a look at both of them and we'll see how long would they actually take. And we find is that one is actually equivalent to linear time and the other to quadratic time. So one is certainly better than the other, but we'll prove that to ourselves. All right, so let's look at what our method will actually look like now. If n, so if the number of elements that we have in our array currently is s.length minus 1, as we only have one space left, then we'll actually create a new array of size. Well, we haven't decided. Either our previous length multiplied by 2, or our previous length plus c, whatever our constant amount that we add to is. Then for everything from I up to n, we'll actually, or rather up to n minus 1, we will copy everything. So from the very first thing up to the nth one of index n minus 1, we'll copy all of those from our old array into our new array. So if our new array was A and our old array was S, we'll do this AI is equal to SI from the first element up to the last one. Then we say S is equal to A. So we're effectively making S, the variable S, an alias for this new array A, and the old array that S was pointing to now has nothing referring to it, and so that'll be collected by a garbage collector. Then we increment N, and then we simply store O in S and N minus 1. All right? Because we had now created that new space, we store O in that previous space, and we now have our N incremented by 1, so it's standing in that new open space to be able to store things in the next case. All right, so that should make us happy. Now we actually want to compare those two strategies. So we have the option of either incrementing it by a fixed size C or doubling it. We're going to analyze what the total time needed to perform a series of add operations would be, and we're going to look at N add operations. We'll assume that we start with an empty stack that's represented by an array of size 1. We will then either keep adding some number of spaces or keep doubling that array of size 1. Right? We'll call the amortized time for our add operation the average time taken by add over a series of these operations. So note, Tn is the number of time taken to add n elements. Right? We're going to do n add operations, so we're going to add n elements to this array list. That entire time is Tn. What we want to find out is what is the average time for a single insertion. So we're going to calculate Tn for our incremental strategy and for our doubling strategy. Then we're going to divide that by n. That gives us the average time for a single insertion. All right, I trust that makes sense. So for our incremental strategy, we're adding each time C new spaces. All right? So how many times are we going to have to do this? Well, if we had started with that single space array, each time adding C spaces to increase our array, then we're going to replace this array n over C times. As in, we're going to have to add C spaces n over C times to be able to do our n inserts. And that makes sense, right? If we were inserting, let's say, 100 elements, and each time we added 10 new spaces, we'd have to do this 100 divided by 10, 10 times. All right. So the total time taken for these n operations will be proportional to, well, the very first time would be copying how many elements from one to the other. The very first time that we are copying our elements, ignore that n currently, the very first time we'd have to copy the C elements that were currently within our array. All right. Actually, the very first time to assign from one of size 1 would be simply copying 1. Then the next time all C are copied from one to the other. Then the next time 2C, because we've added C twice, will be copied from one to the other. Then the next time 3C will be copied from one to the new bigger one. Then 4C, 5C. So each time we increase our array by C, we're actually copying that larger and larger array into the new larger array. The first time it's C of those, then 2C of those, then 3C, then 4C, all the way up to KC. KC is that n divided by C. All right, so that is, we're going to do this. If we're doing that 100, if we had 100 elements that we're inserting and C was 10, we'll do that 10 times. The very first time, we'd copy 10 of those elements into the new array of size 20. The next time, those 20 would actually copy into the new array of size 30. The next time, those 30 would actually copy into the new array of size 40, and so on and on, until we get that 10th time, and we're copying all 100 elements into our new larger one. Why do we actually create that one of 110? Well, we said that when our array is just about to be full, we'll create the new larger array. All right. And that last time is when we actually copy those n, that first element there, of our sequence, we actually copy all n of those into the new larger array. All right, what is this actually equal to? We see that all the ones after n have this factor of c. We can factorize out that c, and we end up with 1 plus 2 plus 3 all the way up to k. We've looked at the sequence several times. Right? We said that if you add that sequence to itself, that you end up with k plus 1 for each of those elements. And how many of these are there? Well, there are k of them. So it's k multiplied by k plus 1 because there are k terms, each equal to k plus 1. But we had added this sum to itself, so we had to divide by 2. And that's how we end up with this. N plus c multiplied by k multiplied by n k plus 1 divided by 2. All right, if we just substitute back our n's into that, we'll see that we end up with a quadratic time algorithm here. All right, let's just prove that to ourselves. We could actually straight away here substitute back our n. All right, the notation here simply looks at it as order n plus k squared, which is n squared because k depends on a in a linear function. However, if we substitute our n over c for each k right here, we'll end up with n plus n on the outside because it's c multiplied by n over c. On the inside, we have n over c plus 1, and all of that divided by 2. We see that we end up with an n here, and over there. We end up with an n over c here, plus 1, all divided by 2. Okay, that c is a constant, that rate does not matter. What we're going to end up with is this n here, so a linear term, plus some quadratic term here. All right, yes, it'll be 2c at the bottom there, but we're not worried about that. And we'll end up with n over 2 there. We said that this is order n squared. Correct? Lower order terms don't matter, those drop away. Constant multipliers also drop away. So this is simply quadratic time. So when we start from an array of size 1, each time adding a constant number of new elements, or rather, each time adding a constant amount of capacity to our array, some c, then we'll do this n over c times. And if we count up all the copies that we have to do each time, we end up with a quadratic amount of, rather, we end up with a function that has a quadratic growth time. So it's a quadratic function. All right, so great. This is then order n squared. What is the average time? If Tn, which is the time taken to insert n elements, is order n squared, then the time taken for a single one of those will be, as we agreed, Tn divided by n, and that will be linear time. All right, why? Because we divide by n. So we have Tn, which is order n squared, and we're dividing by n. That was our Tn. And we end up with something that is order n time. Okay, we end up with something that for a single insertion, it is then linear time. All right. Do we believe that? Certainly we should. All right. If for all n of them it's quadratic time, then for a single one will be order n time, linear time. Then what about our doubling strategy? All right. So each time, instead of now adding a constant amount, we instead double the size of our array. Again, we'll have to copy everything that was in our old array into our new array, but this time we're doubling the capacity of our array each time. All right, note that we do realize that each time we are, regardless of what size we begin our array at, we are creating either too much space or too little space, depending on what our end size is going to be. We don't know what the size is actually going to be. We don't know, as in we don't know how many elements we're going to add at the end of it, that n. So we're either going to be creating something that's too large or too small. So instead we start with something very small, like 1, and simply double it each time. All right. So we're fine as long as the number of elements that we're adding to our array, small n, is smaller than the capacity of our array, big N. However, as soon as small n is greater than or equal to big N, then our array is too small, right? If we try to add something over that, we'll end up with this overflow issue. So instead, we'll create a new array. The size of our new array, or the capacity of our new array, will then be 2n. Will double what the previous capacity was. All right, then we'll copy everything from our old array A into our new array B. We'll have to do that for everything from 0 to index n minus 1. So the entire size of the entire capacity of our previous array, because it's now full. Then again, we simply create, we let B be an alias of A, and that simply throws away the other one. We can then insert our new element because we have this new larger array. Now, what will be the time taken here? Now, instead of n over c incremental additions of space, now we are doubling our array each time. How many times are we going to do this? Again, a logarithm comes into this. It'll be log base 2n. Why is it log base 2n? Remember that the number of times that we can divide n by 2 is equal to log base 2n. And starting from 1, doubling the capacity each time until we get to n, that will be exactly log base 2 number of times. All right, there's a question before we look at how we end up with the answer. When using the doubling method, do you double once and double again once and the array capacity is reached? Or once the array capacity is reached, or do you double each time there is an addition? No, you only double, just like the incremental, you only grow your array when it's full. So we double it each time the capacity, the current capacity is reached. All right, so if we are inserting n elements, then starting from an array of capacity 1, each time doubling it would take log base 2n times. Think about it, if we start from the largest one and we halve it each time until we get to that 1, that would be log base 2 times. All right, so we end up with is each time that we copy our elements, okay, the very last time will be that n, that's fine. But the first time we're copying one element to a new array of size 2, of capacity 2. When those 2 are full, we copy those 2 to a new capacity, a new array of capacity 4. When that's full, we copy all those 4 to a new array of capacity 8, and so on. All right, we keep doing this until the last one. Why is the last one 2 to the power k? Well, if we look at this first expression that we had here, k equals log base 2n, then another way of interpreting this is either how many times do we need to halve n until we get something that's less than 1, or to what power do we raise 2 to get n? And that's simply 2 to the power k. All right, so that's why we end up with that. Then that's equal to n plus 2 to the power k plus 1 minus 1. Now this jump will actually prove to ourselves, because that's a pretty big leap, that what I've underlined in the top line there is equivalent to what we've underlined in the second line. Is that true? Well, let's take a look. If we represent that sum as a binary number, what would that look like? The first number on the left, the 1, would simply be 1 in binary, right? 1 plus 2 would be 1, 1 in base 2. 1 plus 2 plus 4 would be 1, 1, 1 in binary. 1 plus 2 plus 4 plus 8 would be 4 ones in binary. Because the leftmost one represents 8, then the one to the right of that represents 4, and the one to the right of that represents 2, then the last one there on the right represents 1, correct? So this number will actually end up being a series of ones up to a kth one. Has that helped us thus far? Not really. It's the same thing. We'd have to add up those. We'd have to convert to decimal and add them up. It's the exact same sum. However, if we add 1, what happens to that first digit, the rightmost digit? I add 1 plus 1, it gives me 2, which means that it goes into the next digit, as in I'm adding a 1 here, and I end up with a 0 in that first digit, right? This 1 keeps overflowing to the next one and the next one and the next one. I end up with k zeros and a single 1 there, right? And that is equal to 2 to the power k plus 1, but I had initially added 1, so I'll subtract 1 to end up with the correct number, the number that I began with. Yes, I realize time is up, right? So we'll stop there, but you should convince yourself that this is true. What's another way that we could look at this? If I had a full decimal number, 9,999,999,999. If I were to add 1 to that, because remember, this is simply, let's see what this is, 9 million plus 900,000 plus 90,000 plus 9,000 plus 900 plus 90 plus 9. If I add a 1 to that, each time I will have a full decimal, as in I would have too much to represent as a single digit. I have an overflow of 1 there and a 0 there. I'd end up with as many zeros as I had 9s and a 1 in front of them. Exact same thing in base 2. And so I could represent that number as 1 times 10 to the power, however many they were here. Let's say they were k minus 1. All right, I'll leave you with that, and we'll simply then make the jump from that to 3n minus 1, which will be straightforward for us. But you should convince yourself that that sequence of numbers added up gives you 2 to the power k plus 1 minus 1. All right, so we'll stop there. Thank you very much for your time. We'll meet again tomorrow in WE5.